Hi, everybody. This is the chemistry of life. This is me attempting to teach you just enough chemistry to understand what you're going to need for the biology class you're in, whether it's majors biology or microbiology, doesn't matter. So here we go. So what's chemistry? Chemistry is the study of matter and the forces that impact it. So of course, that begs the question, what's matter? Well, matter has an operational definition that we just say is pretty much anything that takes up space and has mass. The key here is that two things that are made of matter can't occupy the same space at the same time. That's a big no-no. They can't stack in 3D, if you want to think of it that way. Whereas energy can. Right, and then mass, when we define mass is just the resistance to change, right? So let's say that you have a little cylinder here on the table, try to push on it. It doesn't want to move, right? But you have to push on it hard. You have some force, right? And that's going to eventually make it move. So that's what makes this mass, that it doesn't want to move to begin with. All right, if that doesn't make too much sense, well, neither does most of this stuff. So what's energy? And accordingly, we see the forces that impact matter. So in order to understand force, you have to understand energy. So first we say that energy is the capacity to do work. And you're like, all right, what's work? Right? Well, before we understand work, we'll say that a force is just anything that accelerates an object. This goes back to the idea of mass, right? So we're going to take that mass, and we said we're going to apply a force to it. What that means is we're going to attempt to move it. That's all. So a force is just something that tries to move stuff. So then, of course, there's what's work, right? And so really, I don't have a formal word here, so let's add that. Let's go back and say work. What's work? Work is basically moving, accelerating, right? Accelerating mass or matter. Right. So basically you can imagine any situation where mass is moving, where matter is moving because of a force, that's work being done on the object. Okay. So when we talk about biology, in the majors class, we'll talk about this in chapters 8 through 10. In the microbiology class, we'll talk about this a little earlier. Okay, so let's see. So work. There's three basic kinds of work that cells do. We'll talk about this later, but just for now, we say here's a cell, right? So sometimes cells want to move stuff in or out, right? So there's transport work. That's one kind of work that cells do. Sometimes the cell itself is going to move, like say in that direction, like maybe that's an amoeba or a white blood cell. So that's mechanical work. Right, so you walking across the room is mechanical work. You moving your eyes across the screen is mechanical work. All right, and then lastly, there's of course the chemistry of life, right? A being converted to B, any metabolic pathway, right? So we can collectively just call this chemical work, right? And so here we are back to chemistry. So the question here is, what are the most basic building blocks of matter, right? So going back to that idea of the study of matter and energy, well, what is matter made out of? And in physics and in chemistry, but really in physics, we have this thing called the standard model. And the standard model is one of the most accurate, it's the most accurate scientific model we have to date on any topic, which is pretty cool. And most of this stuff goes beyond what we're going to chat about this semester. But for now, we're just going to say that everyday matter is made of atoms, right? Which, of course, you've heard that many times over the course of your life. So what are atoms made out of? You probably also heard that atoms have that nucleus, and they have this electron cloud that floats around them. So the nucleus itself, as we get into it, we also heard these words before, I'm sure. They're made out of protons, which are positively charged, and neutrons, which have no charge. So now we get into a little more exotic stuff, but it's not hard to understand at this level. We'll just say, what are protons and neutrons made out of? And they're turned out to be made out of these things called quarks. The word quark comes from Lewis Carroll's Jabberwocky. It's a nonsensical term because really quarks don't make sense. And they come in flavors and they come in colors. And all you really need to know at this point is that you get a system of three of them. Okay, there's 6 flavors of quarks, but the common ones are up and down. There's up quarks and there's down quarks. And you put two ups and a down together and you get a proton. So now you can understand that a proton, which, proton, P plus, if you want to, whatever it there, or you say, like, here's a proton, a little circle, but really in reality, it's a system of three things. Okay. And those three things are quarks. Two ups and a down give you the proton, two downs and an up give you a neutron. If this is confusing, it is confusing, right? But the good news is we can, zoom back. We can step back and just consider now that system of quarks as the proton or the neutron. Okay, so we don't know what quarks themselves are made out of. Maybe they're made out of something else, but for now we consider them what are called elementary particles. They're a pure substance. You can't get any smaller than quark. Onto the electrons. The electron itself is also an elementary particle. We don't know what electrons are made out of. We do know that there's other types of particles besides the electron. So collectively, we'll just say that electrons are a class of lepton, right? So at the end of the day, all the matter in the visible universe is made out of quarks and leptons. Okay. Now all the other stuff we don't have to worry about. All the other matter particles. So as for energy, what are the building blocks of energy? Well, this is kind of fun. There's three fundamental forces of nature that we understand pretty well. There's the electromagnetic force, there's the strong nuclear force, and there's a weak nuclear force. And then there's gravity over here. And unfortunately, gravity doesn't really fit into any of this. We don't really have the ability to reconcile gravity with other little things. Gravity, doesn't really have any effect on things until you get big enough. You have enough collection, you have a big enough collection of atoms, and then you can start to deal with gravity. So forget gravity right now. We don't have to worry about that. The three forces that we do deal with here, each one gets what's called a carrier particle called a boson. So these things, these bosons, these bozos, can pile on top of each other. So you can occupy the same place at the same time. Just picture a light getting brighter and brighter, and that's the basic idea. All right, so the photon, you've probably heard this word before too. You can now pin it somewhere in your head. The photon is the force carrier of the electromagnetic force. Electricity and magnetism, they are forces of nature that when you go all the way down to the smallest part, it is a photon. You don't get smaller than a photon. What are photons made out of? We don't know that either. They're photons. Okay, and so this stuff governs everyday life. All of the everyday stuff you deal with, whether you're driving in your car, eating your dinner, going to bed, whatever, watching TV, using any technology, it's all governed for the most part by the electromagnetic force. Deep, deep, deep inside the nucleus, there's a much stronger force called the appropriately named strong force, the strong nuclear force. And this is what holds the nucleus itself together. Okay, so that force particle is called the gluon because it glues the nucleus together. Not very imaginative, but it's fun. And so the proton and the neutron, or proton on proton, plus charge here, or neutron, neutron. Okay, it doesn't matter. Protons and neutrons all stick together with these gluons. Okay, so you can think of a carbon nucleus, just for example. Carbon has an atomic number 6. 1, 2, 3, 4, 5. There's 6 protons there. Okay, but plus charges don't like each other. So you can imagine if there were just the protons, these things would be flying around, flying apart from each other because of that repulsive force. But good thing we got neutrons. The neutrons kind of keep it together, right? So the neutrons are sort of the arbiters of the positive charge from blowing itself apart. And that's why the nucleus is kind of complicated. All right. So, and then to make things even weirder, there's something called the weak force, the weak nuclear force, which ironically is stronger than than gravity, rather. But again, we don't worry about gravity. The weak nuclear force is responsible for radiation, and that's as much as I'm going to tell you. And the force carriers for this are called the W and Z bosons. So the weak force is kind of a weird force to understand, and most physicists have a poor job even explaining this. So really, it's all for us about this. Okay, so if everything confused you a little bit right now, that's okay. It's nice to hear that stuff at least once in your life so you can get like a deeper understanding of the universe. But for the practical stuff, we're going to deal with the electromagnetic force. So this is that familiar force that governs the electron and the proton, attracting each other. the electrons repelling each other, right? Those things push each other apart, and same with the protons pushing each other apart. So you've all heard, like charges repel, opposite charges attract. That's all about the electromagnetic force, right? So, but the rest of this stuff, this weird stuff, so there's the proton and the neutron and the electron, right? The E is the electron, and then you got the ups and the down quarks, and those form the protons, neutrons. All the other stuff there, you got, and here are the force carriers, right? So there's the photon, there's the gluon, I'm sorry, there's the gluon, there's the photon, there's your Z and W bosons. And you got this thing over here called the Higgs. This is a brand new kid on the block. The Higgs boson is a particle that helps us understand why mass exists. It's a field that fills the entire universe, kind of like Star Wars' force. And it gives the ability of these guys over here to have mass, to be dragged, right? That's the idea. But you don't have to worry about that. That's just, if you've ever heard of the God particle or the Large Hadron Collider or the Higgs boson, there it is. It takes its place up here. Okay. And then the other weird things here, these are all experimentally verified, but they only exist for short periods under artificial conditions. So you don't have to really worry about any of this stuff here. And then there's neutrinos. You probably heard the word neutrino. Neutrinos are in the same class of thing as electrons, really, really small, really, really light. And there's 65 billion of them passing through every single square centimeter of your body per second. That's kind of crazy. Really, we don't know what they do. I don't know what they do. Maybe somebody does, but whatever. So let's get back now to the atom. That's all we're going to talk about for the rest of this year. So an atom is a system of protons, neutrons, and electrons in some kind of particular arrangement, right? So we'll learn that we have this dense nucleus, which is made out of the protons and the neutrons. And then we have these much less dense, fluffy electron clouds. And the electrons are arranged around the atom at different energy levels and in different patterns. So the energy levels we call shells. Think of this as, if the electrons are rubber band, right? Imagine like a limp rubber band versus like a really tight rubber band around maybe 2 nails, right? So this guy's loose, he's low in energy. This one's really tight, he's high in energy, right? So watch this. Here, take a board of wood, put a nail in the center, and then take a rubber band and like put it around another nail over here. And then take another rubber band and pull it really far and put it over here. Okay, so you can understand now that this rubber band isn't very tight. This one's pretty tight. All right, so what I could do now is imagine I took this nail right here and I kind of just did a circle of it. All right, so that rubber band could be anywhere in that circle and have the same amount of energy in it. Likewise, that outer one could have even more energy in any place in that circle. So that's the idea of the energy level or the shell. All the electrons within a given shell have the same amount of energy. All right, that's all I'll say about that for now. So how are atoms distinguished from each other? When we look out into the universe, when we look at, just right outside our door, we can see that there's different kinds of atoms. And what makes one atom different from another atom, there's one fundamental property, and that is the number of protons that is inside that nucleus. Not the number of neutrons that are in there, but the number of protons, not the number of electrons that are around the cloud of that nucleus, the protons. It is the most important number. It's such an important number that we define the elements, the families of atoms with similar numbers of protons. With this number, we call this the atomic number, right? So there's carbon over there on the right, and we can see it has atomic number 6. There are 6 protons in the nucleus. Now, remember I told you earlier that so here is this a proton and this is another proton, right? They don't like each other. They're going to repel each other, stick a neutron in between them, and then glue them all together. And that's how we can start to build larger nuclei beyond hydrogen, which is atomic number 1. Well, okay, so we can't just have protons. Instead, we have to have neutrons and protons. And that's what this mass number is. The mass number of a given atom is how many total particles are in the nucleus, not just protons. And that's why it's always going to be a bigger number than the atomic number. All right, that makes sense. So carbon, we would call this carbon 12, right? So here's an atom. let's just pretend that's an atom. And that atom has protons, neutrons, and electrons. That atom has 6 protons and 6 neutrons for a total here of 12. So we're going to say carbon 12. All right, now here's the kicker. Some atoms have more neutrons than others, but the same number of protons, right? So imagine I just plucked another atom out of the air, and this one I was able to peer in there, and I saw, sure enough, it had 6 protons, and it had 8 neutrons for whatever reason. So it's a little heavier, a little more massive. This is carbon 14, right? And so carbon 14 and carbon 12, these two atoms, this atom right here of carbon 12 and this atom here of carbon 14, are both carbon, right? And so when I'm classifying the different atoms, when I put them into categories, I'm going to put these two atoms in the same place of whatever I'm going to do. We're going to learn about the periodic table in a bit, but just, picture there's a little bucket right here, and we're going to dump a bunch of carbon atoms in there. And every single atom that we observe, we put in there, that's got 6 protons, right? And so we're going to say that this is a family of atoms that are in the same place. And that's what the word isotope means. So all atoms are an isotope of a given element. In this case, we have 2 isotopes. We have the carbon 14 isotope and the carbon 12 isotope of the atom carbon. Okay, let me say that better. These are 2 isotopes. These are 2 atoms of the isotope. No, that doesn't work either. Okay, let's say it this way. Here's carbon 14, here's carbon 12. These are 2 atoms of the element carbon, right? They're 2 different isotopes of the element carbon. Right, so now I'm using that word element a lot here, right? So now we're going to understand what they mean by element. So the element, think of elements as families. An element is a family of atoms that all have the same number of protons. And within that family, just like in your family, there are variations, but you're all in the same family. So you're all in the same place on the chart. And that's what the isotopes are. Okay, so the only thing that actually exists in the real world is an isotope. Here's an atom of carbon. Well, which isotope is it, you would ask, right? It has to be one. It has some number of neutrons in it. And so it has to be either or. It's got to be somewhere in there. So it's got to be an isotope. So the isotope is the thing that exists in the real world. Okay. All right. So let's see. Yeah, that's it. I think that's so. Let me just summarize that. You have the atomic number, and that's the number of protons, and that never changes for an element, right? If I say 6 protons and I add another 1 to 7, I'm not carbon anymore. I'm something else. I'm nitrogen. Okay. So atomic number, that's most important, and then you have the mass number, or the atomic mass, and that's the total of the protons and the neutrons. That can vary based on the number of neutrons. Okay, now one question you might have in your head, let's go back to, we got carbon 12 and carbon 14. Right, here's carbon 12, here's carbon 14. You might ask, like, what's different between them? And what I'm going to tell you is, for the most part, the isotopes of a various element have exactly the same chemical and physical properties. Okay, they're a little more massive, right? This is a little heavier than this, and that does come into play in certain physical things. But for the most part, for our purposes, we can just assume that all the isotopes have the same exact chemical and physical properties. Okay. So now the question is, how are atoms distinguished from each other? And the key here is, because they have different numbers of protons, they're going to be able to attract a different number of electrons. And those electron clouds, the shapes, the configuration, the nature of that electron cloud is what determines the physical and chemical properties of a given element. So you can see here on the left as an example, that is a block of sodium, which is a very soft, malleable metal. It's also very reactive. You can see that's why the guy's wearing gloves. And but it's a solid room temperature, and it's a metal, but it's a very weak, soft metal. You can see it's being cut by a knife. In contrast, chlorine, another element, you can see is a gas at room temperature, also very reactive. Right? And you can also imagine what would happen if we put sodium and chlorine together. You've all seen sodium chloride, which is table salt. not very reactive and essential to life. Okay, so the take home here is that the electron configuration around an atom's nucleus is what gives it its unique properties. This next slide here explains how we name atoms, right? So what makes them different from each other again and how we name them. So all atoms with the same number of protons, they have the same atomic number, they will have essentially the same physical and chemical properties. Said that already. They're arranged into families called elements. Each element family has different properties, right? So carbon has different properties than, say, gold. The atom happens to be the smallest unit of matter that retains these properties. The atom is the smallest unit of an element that is still considered that element, right? Any smaller than an atom and it's just a proton or a neutron or an electron, it's no longer carbon. Okay, so atoms themselves cannot be further broken down into other substances by ordinary chemical reactions. There's nothing you can do in the lab, mixing beakers and heating things up, freezing things, putting them under pressure, and changing atoms themselves. Okay, chemical reactions are essentially atoms being shuffled around. The word atom itself comes from the word atomos, which literally means indivisible in Greek. Now, we know atoms aren't indivisible. We know we can break the nucleus, but that requires high levels of energy that go well beyond ordinary chemical means. And we call that particle physics. And we're not going to talk about that at all. So let's not worry about it anymore. It turns out that the atoms in our everyday universe that we can observe fall into 92 naturally occurring ones. There's 92 naturally occurring elements. We've artificially created more than that. But when we look out there in the universe, we only find 92. And so we have these 92 families that are all very different from each other. And one observation that was made was that as you go up in atomic number, you start to realize that patterns begin to repeat themselves. So in other words, a chemical property of, hydrogen might end up being seen again and seen again and again and again. And so the idea here is that if we arrange the elements according to these properties, we get a periodicity. In other words, we see the regular emergence of similar physical chemical properties over and over again. And so what we do here is we arrange these elemental families according to these properties. Okay, and so we have columns called groups, and we have rows called periods. Okay, so periods and groups. Okay, so a group of elements like hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, we can see all of these will have similar chemical properties in one way or another. Okay, going along this way in these periods, so you can see the first period has just hydrogen and helium. The second period has lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Each one of these periods corresponds to the fact that the elements, the atoms of those elements in those periods all have electrons in the farthest part of their region, the farthest ones on the outside, we call those the valence electrons. They're all in the same configuration. Okay, and as we'll see, we'll see that there's different shells. Remember the rubber band idea with take two nails, put the rubber band around it, right? So we're going to see that there's shell 1, shell 2, and shell 3. Those are the most common ones that we'll deal with. Shell 1, shell 2, shell 3, right? And we'll see that there's 1 electron in shell 1 for helium, hydrogen, and 2 in helium. And then lithium will have all of those electrons that helium does, plus another one. Okay, so we'll get to this later. I'll show you the electron configuration. But for now, just understand that the way we classify the atoms is along this table we call the periodic table. Okay. So let's go back here. I know there were some words that I glossed over. Let's see. So, well, I said all this, right? So the periodic table arranges elemental families based on similar properties, chemical and physical. Each column is a group. And a group by definition contains elements that all form the same number of bonds and other properties. So they have chemical, physical, and chemical properties. Whereas the periods contain all the elements that have their outermost electrons at that same energy level. Okay, and so the reason why there's no elements in these spots here is simply because the first energy level can only hold 2 electrons. 1, 2. Okay, so if we put helium over here, there is no 3, 4. It just makes no sense. That's why there are these weird gaps, right? The second shell and the third shell actually both hold 8. And so that's why you can see 1, 2, 3, 4, 5, 6, 7, 8. There's 8 elements here, and there's 8 elements here, right? So you can see that there's this big gap here because we can only hold 8. The fourth shell can hold a whole bunch. And you can see the fourth, fifth, sixth, seventh, they can hold a whole bunch of electrons. And that's why we have this strange pattern here. All right. So now we can ask how are atoms actually organized? And we can start to get to the heart of it. And you can see here on the far right, here's a nice model. You can see the very, very, very far deep part in there. That's the nucleus. And you can see that the nucleus is about 1 femtometer in diameter. All right, and you can see here 4 particles. So this is helium. This is the nucleus of a an artist's version of a nucleus, helium. You can see that there's these are probably the neutrons holding apart the protons. All right, so here's 2 protons. They're not near each other. Okay, instead the neutrons. So those gluon things are sticking them together like that. And that's the nucleus of helium. And then you can see there's this big blurry black fuzzy sphere, and that represents the electron cloud, right? So the take home here is that the nucleus is very small, very dense, surrounded by a very large, very wispy sort of cloud, right? And that cloud, I want you to, by analogy, think about driving in the car, looking at another car driving and looking at the hubcap and notice it's blurry. Right? It's fuzzy, it's hazy. So the electron cloud is just, we can't catch exactly where the electron is at any given time. It's somewhere in that cloud. So you can think of it as a probability cloud. You can't know exactly where the electron is at any given moment. Or if you do, then you don't know what shell it's in. You just know it's right there. And that's called the uncertainty principle. And that's also something you might learn about in a physics or a chemistry class. All right, over here, you can see 3 of the most common elements to life, hydrogen, carbon, and oxygen, and you can see their corresponding number of protons. So hydrogen's got 1, carbon's got 6, and oxygen's got 8. So now we start to build this framework of how atoms are built, we can start to understand the rules. So the protons, because they're positively charged, attract negatively charged electrons. And because the different elements have different numbers of protons, they're going to have a varied number of electrons. And so if you have a varied number of electrons, that's where the varied chemical and physical properties come from. So now let's talk about electrons themselves. Let's focus in on just electrons. So electrons, because they are these quantum particles, these little subatomic particles, they have specific characteristics. And here's 3 of them that we can really care most about when we deal with biology. The first one is called spin. You can imagine an electron spinning either clockwise or, counterclockwise or clockwise. All right. So that's spin. You can also denote it as either up or down. All right. So there's a spin there. They always have a charge of -1. That doesn't change, but that's a property they have. And then they can exist at some amount of energy. So they have an energy level, and that's a very specific number. It's like 1 or 2 or 3. Those are the only ones we're really going to be dealing with. There's 4, 5, 6, 7, 8, 9, 10, whatever. But the energy levels for everyday life for biology are just 1, 2, and 3. Okay, so for a given electron, there's going to be a spin, there's going to be a charge, and there's going to be some kind of energy level, right? So if you look over here, these are the 3 energy levels, these 3 here that we're talking about. These are imaginary boundaries around a nucleus, right? So you have the first energy shell, you have the second energy shell, and the third one. Why do we call them shells? Well, I want you to really picture these as 3-dimensional hollowed out spheres. Okay, they're 3D spheres and they're imaginary. What do I mean by that? Well, imagine here's the sun and here's the earth. And we know that the earth goes around the sun, right? But what I want you to do is remove the earth, right? The orbit's still there. It's just invisible. It's just the path it could take. All right. And so that's just a line. Now imagine that as a sphere, right? From a side view of here's the sun, here's the earth, there's the plane of the orbit. Imagine an entire sphere now. And any point the earth could be, anywhere on the edge of that sphere, and it would still be in that shell. Okay, so that's an energy shell. And there's 3 of them around the atoms that we deal with in everyday life. Okay. So because they're mass particles, electrons can't occupy the same space at the same time. What that means is they can't have the same quantum numbers. They can't have the same spin and charge and energy. They just can't do that. Okay. And so this is the rule. These are the rules of the RIP. This is how we understand how we build the electron cloud around the atom. The first rule is that electrons always pair in opposite spins. In other words, if there's one on the first shell that comes along and it's up, the next one that comes in is going to be down, right? And so we'll call that an electron pair. That's when electrons are in their most stable state. And what that means by stable, when I say stable state, it means they're not going to try to react with things, right? Nothing's going to happen. Okay, so paired electrons are boring. That's the idea there. The second rule is we're going to fill the shells from the lowest to the highest, right? It's just like if you were packing a box, you're going to put stuff at the bottom first, then in the middle, and then at the top. All right. The only one, so again, think of a box. Think of a box, after you were moving or whatever, you piled a bunch of stuff in it, right? In order to react with that box, in order to just like pick stuff up or whatever, you're going to interact with the stuff that's on the top, right? You're not going to easily get to the stuff on the bottom. You can't do that. In the same way, the electrons on the outermost edge of the atom are the ones that are going to experience forces and bonds. And so we call the outermost shell the valence shell. Valence is the Greek word for strength. It's how strong an atom can react. That's one way to think of it. So let's see. So outermost ones, yeah, though I said all this already. All right. So building an atom, we're going to take the atomic number. That's the number of protons. And that's going to give us a starting point. That's going to tell us how many electrons come along with the atom to begin with. And we're going to take that number and we're going to say the first 2 go into that first shell. Because remember, we said earlier that the first shell here can hold 2 electrons. And then the next one can hold 8. And the next one can hold 8, right? So 2, 8, 8. This is called the octet rule. You might have heard that before. Right, so we're going to use the atomic number to determine the number of electrons. Then we're going to fill the shells from lowest to highest. And each shell, so each shell holds a different number of electrons because they're bigger. Think of little buckets and then bigger buckets. So the first shell only holds 2 electrons. And then the second and the third shell hold 8 each, which you can see here. So an electron in the first shell, energy level 1, is going to have less energy than an electron in the second shell. It's going to have less energy than an electron in the third shell. Okay, and you can pump electrons with energy. So you can take an electron on that first shell, pump energy into it, right? Photons. You can shine photons on this, and that electron will absorb those photons and jump up to the next energy level. It's called quantum leap. But then it's going to fall back down. And as it falls back down, it's going to give off that energy again. And this is the basic idea of how light bulbs work. Right? You send electricity into the bulb, the tungsten absorbs the energy. It jumps those electrons up, and then when they come back down, they give off a photon. And now we're going to explain what an orbital is. An orbital is the shape, the actual shape of what the electron's doing inside that shell. Think of them like vibrating 3-dimensional waves. So we're going to start to visualize electrons now. How do we visualize the arrangement? Well, there's two ways to do it. There's an easy way and a hard way, and we're going to deal with the easy way almost exclusively, but I'm going to explain what the hard way looks like. So the easy way is, which is not accurate, but the easy way is called the electron configuration or electron distribution diagram. Okay, and the idea is, we'll do it as an example here. Let's do oxygen, which has atomic number 8, right? So it's got 8 protons. So here's the first shell. All right, and remember the rule, the first shell holds 2 electrons, right? So we're going to take 2 electrons away here to get 6. So here's 1 and 2. And notice I drew them right next to each other because they like each other. They're paired, right? One's up, one's down. You don't have to draw the up and down thing, but there they are. There's the first one. And now we draw the second shell. This is the second energy level. And I told you that can hold 8, but we only have 6, right? So here's what you do. You go 1, 2, 3, 4, 5, 6. So you can see these two are happy. You can see these two are happy, but then this guy's lonely and this guy's lonely, right? So you can imagine there's a slot right here and there's a slot right here because electrons like pairing. That's just a rule you have to understand. Electrons like to pair. And so you would say that oxygen here, O, can form 2 bonds. We can put another electron here and another electron here. Okay, so hey, let's do hydrogen. Hydrogen's got atomic number 1, so it's got 1 electron. So here's hydrogen. Well, isn't that perfect? Hydrogen can just come along here and put its electron there. And what that would look like would be this. Right? There's the nucleus of hydrogen. There's the nucleus of oxygen. And let's do the same thing over here. Let's put an electron here, and here's hydrogen. And there, we just built H2O. There's water, which we'll talk about a little bit more later. Right, so these are electron distribution diagrams. And by the way, because both atoms are sharing that pair of electrons, this is called a covalent bond. And since we're here, I'll explain that because the nucleus of oxygen has a little bit more of a stronger pull on electrons, it has a higher electronegativity. All that means is that electronegativity is simply the property of a nucleus in which it tugs on electrons. So some atoms, some elements will tug on electrons more strongly than others. Okay, in this case, oxygen tugs on it more strongly than hydrogen. So if I was to redraw a water molecule like this, here's a water molecule. So we would say, there's the oxygen over here, and those two little things here are the hydrogen. The electrons that are shared around this big 3D sphere they tend to be on this side more. And so we're going to say that side of the molecule has a slight, that's a delta, it's a lowercase delta. Here's a capital delta, here's a lowercase delta. These are Greek letters. Delta negative. And over here we'll say delta positive. And what this means is partial charge. The water molecule itself has the same number of protons as it does electrons. This is not an ion, but they're not shared evenly. So you could imagine drawing a line kind of through it like this, where that's more negative and that's more positive. So you would say that this molecule is polar because it has an uneven distribution. And so this kind of bond is called a polar covalent bond. In contrast, if these were 2 hydrogen nuclei, and those 2 hydrogen nuclei were sharing a pair of electrons perfectly evenly, this would be a nonpolar covalent bond because those electrons are being shared perfectly evenly between the 2 nuclei. If 2 atoms come together, let's do sodium chloride now. If 2 atoms come together, here's chlorine and here's sodium. Chlorine's outer shell has 1 missing electron. So it looks like this: 1, 2, 3, 4, 5, 6, 7. All right, so this inner shell's full. The inner two shells are full. This is the third shell, and it needs one more electron to fill its valence shell. Sodium has just one measly electron out here in its third shell. And so sodium is going to just donate its electron to chlorine. And so now chlorine has a full valence shell, but at what cost? It's now negatively charged. It's got a -1 charge. And likewise, sodium has a +1 charge. They're not sharing the electron, it donated it. And so there's no sharing here. But because this is -1 and this is +1, these two things will attract each other. And so this is called an ionic bond because these are two ions. And that's the basics of bonding. Okay. So going back to the electron distribution diagrams now, you can see here, let's define these words formally now. So the shell itself is this imaginary boundary, and all electrons within this boundary have the same amount of energy. Whereas the orbital is the actual three-dimensional trajectory of an electron within the shell. Okay, so you can see here, this is the 1s orbital. This would be the 2p. You know what? Don't worry about that. Let's be on the scope. You'll learn all this if you take a chemistry class, and if not, it's no big deal. The idea is simply that electrons occupy physical 3D spaces and they can stack. You can see here, there's different shapes all stacked in the same basic area. And the higher you get in terms of the number of protons, the more and more exotic these shapes become. Okay. So orbitals themselves are always pairs of electrons. And so those shapes become more and more different. So okay, beyond the first shell, right? If this is shell number 1, the first energy level, I told you earlier, it can only hold 2 electrons. So that's easy. The first orbital is just a sphere. It's just this 3D sphere. The electrons can be found in any place in that 3-dimensional sphere. The second energy shell, which I told you holds 8 electrons. Okay, how many orbitals would that be? Well, remember, each orbital is only 2 electrons. So there's going to be 4 different orbitals, and here they are. The first one is called the 2s orbital, and it's basically a sphere with a hole in the center of it. That hole in the center is probably the 1s. And then there are these pi orbitals that look kind of like figure 8s, like this. And there's one in the y direction, there's one in the x direction or axis, and there's one in the z. So there's 3 dimensionals, right? So there's an x, a y, and a z. X, y, z. Okay, and so you merge all of those together, the spherical one, and then x, y, and z, put all that together, and that's all 8 electrons that occupy that second shell. And so you can see here down at the bottom, these are some 3D standing wave shapes of what electron clouds might look like. And you can see that there are different shapes. These are like different Lego building blocks, right? You can see like this one here, that's probably carbon. And you can see it looks like a tetrahedron. It looks like a 3-dimensional pyramid, right? Or let's draw that a little better. Like this, right? Whereas this one, this looks like a flat triangle, right? So some shapes are like a really cool 3D shape. This one kind of looks like a weird bubbly sphere, right? This one kind of looks like a long cylinder type of shape. Same with this one, right? So the different shapes give rise to different properties. And that's where the different physical and chemical properties come from. So here are some sample electron distributions for the elements most common to life. You got hydrogen, atomic number 1, carbon 6, nitrogen 7, oxygen 8, and then here's sodium at 11, phosphorus at 15, and chlorine at 17. Okay. And so you can identify, so here, what I want you to do, just practice here, is look at the valence clouds, look at the valence electrons. How many valence electrons do each one of these have? And so go ahead, pause the video and fill that in and give me an answer. Okay, so here they are. Hydrogen's just got the 1. Carbon has 1, 2, 3, 4. Nitrogen has 1, 2, 3, 4, 5. Oxygen has 1, 2, 3, 4, 5, 6. Sodium has 1. Phosphorus has 2, 3, 4, 5. And chlorine has 2, 4, 6, 7. Right now, the next question I want you to ask is how many bonds, how many covalent bonds or ionic bonds can be formed by the element? Okay, so pause it and try to answer those questions. All right, if you're back, so here we go. Hydrogen can form 1 bond. Why? Because the first shell can hold a total of 2 electrons. And so there's its second bond, or there's its second electron. So it's 1 bond it's sharing. Carbon can form 4. Why? Because that second shell can hold 8 total electrons, and it currently has 4. And so 8 minus 4 is 4. Nitrogen can form 3. Why 3? Because again, that second shell can hold 8, and it currently has 5 there. And the difference there is 3. And so along those same lines of reasoning, oxygen can form 2. Okay, now sodium here, you're like, oh, well, sodium can form 1, 2, 3, 4, 5, 6, like 7 bonds. But here's the thing. It's much easier from a thermodynamic standpoint, from an energy standpoint. It's much easier for sodium to just give this one up. Because think about what happens. Without that electron, it now has a full complement of electrons, and it's now new valence shell. Right? And so that's why sodium is actually going to just give up that electron. It's not forming covalent bonds. It's going to form an ionic bond. Generally with over here with chlorine, right? Because look at chlorine, it can form a single bond right here. And so it basically just gets that electron. And then this being a negative charge and this being a positive charge, there's your ionic bond between the two. Now, phosphorus does form covalent bonds because notice it's got 2 here, 3, 4, 5. So it has 5 valence electrons, and it's not really easy for it to lose all of those electrons or to gain, to grab 3 electrons. So what it does instead is it does covalent bonds. It can form 3 bonds here, and that will give it a total, a full valence shell. So that's that. So one idea to think about is unpaired electrons in that valence shell give rise to an atom's tendency to react. The rule of thumb is if there's an odd number of electrons in the valence shell, it's much more reactive than if it has an even number, because electrons like to pair. Pairs are even. Right, so if we go back a slide here, you can see oxygen has these 2 pairs, right? But it has these lone ones. But it's got an even number, right? 2, 4, 6. It's got 6 electrons there. Whereas nitrogen has 7, right? So in some cases, oxygen, these 2 electrons will occasionally pair together, and you'll just have this big gaping wound here. Oxygen, this is part of the reason why oxygen is complicated and is one of the reasons why we breathe oxygen in for energy. There's a lot of weirdness with oxygen's electron cloud that we're not going to get into. But you could say with nitrogen, okay, because of that odd number, nitrogen is going to be much more reactive with oxygen. And hydrogen is going to be much more like hydrogen is so reactive, it doesn't even exist like this in space or anywhere. It doesn't exist anywhere. And in fact, these 3 elements can all react with themselves, right? So you have H2, which would look like this, right? It would, well, let me draw that better. You got H2, that forms a single bond. You got N2, here's H2, you got N2, and that forms a triple bond. There's 3 shared electrons here. And then oxygen, O2, shares 2, right? So you can draw them like this. Here's hydrogen, hydrogen. Here's nitrogen, 1, 2, 3, nitrogen, triple bond. Here's oxygen, double bond oxygen. Collectively, these are called the diatomic elements because we never find them by themselves. Okay, and so the valence of an electron, I'm sorry, the valence of an element, not its valence shell, not the number of valence electrons, but there's this, just we call it its valence. It's a loosey-goosey way of just talking about how strong it is. In other words, how likely it is to react. Okay, and so you can compare, for example, chlorine and carbon, right? So carbon forms graphite. You know, you can draw with the pencil, right? That's what graphite is in the pencil. It's not very reactive. It's very safe. Whereas chlorine, because it has that one unpaired electron, that odd number of electrons in its valence shell, it is very, very reactive, and that's why it's toxic. Basically, anything that chlorine bumps into, it's going to strip an electron from. And that's going to cause other things to be reactive, and that can cause a chain reaction. So that's that. Now, the next few slides give you the in detail about bonding. And I think this might be in the way here. I'm just moving a zoom control over, right? So we can formally talk about bonding now. I already gave you this a little bit, but let's give it to you again. So atoms in a molecule attract electrons to varying degrees. And that amount of varying degree is determined by its electronegativity. Right? So the atom can either strongly or weakly or somewhere in between tug on another atom's electrons. And that property is called its electronegativity. So the more electronegative an atom is, the more strongly it will pull on electrons. And so we can look at hydrogen, carbon, and oxygen. And we already went through this, but let's just see it again. We can have one chemical bond here with hydrogen, right? And so you can imagine if this is hydrogen with atomic number 1, here's another one with atomic number 1. These come together and the two are shared like that. And there's your covalent bond. Okay. This is also the beginnings of a silly face. Okay, that's me going on a silly tangent. There's his ears. And he's an angry baby or something. I don't know. He has to wear his mask to school. Ugh, okay. So anyway, get the idea here. There's oxygen can form 2 bonds, carbon can form 4 bonds, and you can see argon here. Argon is one of the noble gases. You can understand now why noble gases are noble gases. They don't react. I guess there was something about being noble meaning not being reactive. I don't know. But it doesn't engage with the rest of society. It reserves itself away from society. Maybe that's what they mean by noble. It's happy as it is. It's got a full valence shell. All the electrons are paired. It's electrically neutral. This is as good as it gets. Okay, now I said electrically neutral. What do I mean by that? It's got the same number of protons as electrons. All right, so there's 2 basic rules that all atoms obey. So let me just formalize this. So the first is, I said electrons always pair, right? That's the most important one. And then you have the atom wants a full valence shell. And that's the second most important. And the third is atoms want a neutral charge. Neutral charge. That's the least important. In other words, if there's an unpaired electron, it's going to attempt to pair with something. And we're going to keep doing that until we have a full valence shell, even if it means gaining a charge, like what chlorine does or what sodium does. And then once it gains that charge, it will look around for other atoms in an attempt to neutralize that charge. Okay, so let's look at, well, let me go through the slide here. Valence electrons, those are the ones on the outside. They're exposed to the environment. The different elements have different valence electrons, and so they are stable when they're full. I said that already. You got to know what gases, right? So how do they fill their valence shell? They either steal them or they share them. And so here we go. Here's sodium and chlorine. Let's, oops. Oh man, I just pushed the wrong button there. Let's try that again. Okay, so here's sodium and chlorine. You can see that chlorine needs the 1 and sodium wants to get rid of 1. And so very easily, sodium's going to put this electron out here, chlorine's going to steal it, and then they're both going to be charged. And as a result, they're going to attract each other, right? So here's sodium giving its electron to chlorine. Here's chlorine having it. It has its full shell, right? So here's the thing. Here's the kicker or the key. Chlorine now has a full valence shell, even though it now has a charge. Why does it have a charge? It has more electrons. It's got one more electron than it does protons. Sodium's in the opposite problem. Sodium has one fewer electron than it does protons, but they're both stable in that respect. So to resolve or neutralize that charge, they stick together. Okay, and so that new molecule, that system of atoms, this one system of atoms, the sodium chloride atom, sodium chloride molecule, is itself neutral because it consists of 1 plus and 1 minus. Okay, so rule 1, fill the valence shell. Rule 2, deal with your charge later. And that's the basic gist of how we build more complex molecules. Okay. The key to why it's ionic and not covalent, not polar covalent, is when that electronegativity is dramatically different between the pair, between the element pair, between sodium and chlorine in this case. If it's extremely different, you go from being a polar bond where one's unevenly being shared to stripping it completely and having an ionic bond. Right? Stealing an electron, you change the charge, you go from a neutral atom to a charged atom, and the charged atoms or molecules are called ions. And that's why we call this the ionic bond. Okay. All right, we already talked about covalent bonds, so I'll gloss over this. But here's formally, here are the diatomic elements, right? So the key here is that you can share one pair of electrons, or you can share 2 pairs of electrons, or you can share 3 pairs of electrons. Right, let's just draw that out so you can see that more clearly. So here's let's do nitrogen, atomic number atomic number 7. So you got 2 here, that's the first shell, and then 3, 4, 5, 6, 7. Right, so it has 3 unpaired electrons here. And so here's another nitrogen, 1, 2, and then here's 1, 2, 3, 4, 5. Right, so you can see they'll share these, they'll share these, and they'll share these. And so if we rearrange all this, we can imagine there's the triple bond. Okay, plus the other 2 over here. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 6, 7, 8. So they each have 8 at any given moment going around their valence shell. So that's the triple bond. Okay, and by the way, as you share more and more, it's stronger and stronger, right? So this is a weak interaction compared to a stronger one, compared to very strong. This is so strong that biologically, this is essentially inert for us. We humans, all animals, don't break that nitrogen bond, despite the fact this being about 70% of what air is made out of that you're breathing in. Okay, there are some critters that will break this bond. They're called nitrifiers. You have like nitrification going on in bacteria, mostly. It's mostly bacteria. And that's all I'll say about that. So here's just some fun visuals. You can see on the left here a Bohr model. This, it doesn't actually look like that, but it's nice and easy to visualize. But on the right here, that's a much more realistic view of the 2 1s orbitals coming together and forming what's called a hybrid orbital. We can visualize molecules in different ways depending on what our goal is, right? If our goal is to just convey the ratio of the different elements, like 1 part carbon to 4 parts hydrogen, we have what's called the molecular formula. This is the most common way of writing things out. Like if you want to write out glucose, you would say C6H12O6, right? The key here is that these have these constant ratios of the elements. So molecular formula is nothing more than giving you a tally of the ratios between the different atoms. The structural formula gives you a little bit more information. It's not easy to draw this in, say, Microsoft Word if you were typing something out. So it's a little harder to display, but it's more informative. It gives you not only the ratios, but it particularly shows you the arrangement in an atom structure. So you can start to see now, for example, double bonds, whereas you can't, there's no information here to suggest, if you know what you're looking at, you can imply the double bonds, right? But here you don't have to imply anything, you can see them, right? And so the structural formula is the second most common and pretty useful way of displaying things. This is actually what we'll be using all semester, generally. Right, we're not going to usually use a ball and stick model, which gives you not only the layout and the display, but now we have 3D. We can see, for example, the tetrahedral model, that triangle of the carbon arrangement. We can see that a single bond gives us two tetrahedrons touching their heads like that, whereas a double bond, that's a plane. This is a flat surface. And you can only really understand that by looking at the ball and stick. The space film model is generally the least useful, but it's the most accurate representation of what molecules look like in real life. So this would be like the shape of the electron clouds around that molecule, right? But, compare these two, you really can't see that double bond, right? So the utility of the space film model when you're dealing with important things like how many bonds and whatnot, it's less useful. Right, and that's why the structural formula is the most common way of portraying chemicals. Now, there's one other way that we portray things in organic chemistry, which is generally things that are mostly carbon and hydrogen. And so here, watch this. Let's say that I want to draw a really long carbon chain. I could do this, which this will take some bit of time. And then it's a hydrocarbon chain. So there's 3 hydrogens here. And then there's another 2 here. And there's another 2 here, right? Because carbon forms 4 bonds. And so, but look how long this is taking me to do. This is kind of getting boring already. And I'm sure you're bored watching this, but there we go. Just to prove a point, there's how many carbons are here? We got 1, 2, 3, 4, 5, 6, 7. We got 7 carbons, right? So this is whatever, the septane. Watch this. 1, 2, 3, 4, 5, 6, 7. There we go. I just drew the exact same molecule. Anybody who's trained in reading these kinds of diagrams will see that those are equivalents, right? So the rule of thumb here is the vortex, or I'm sorry, the node, that's carbon. And then you see how they're single lines. That denotes that these are single chemical bonds. These are single covalent bonds. And so what's implied here that's not shown is these 2 hydrogens here, these 3 hydrogens here, these 2, these 2, it's all implied. And so it makes it way simpler and easier to draw complicated things, right? So for example, here's benzene. There you go. Okay, here is a hydrocarbon chain that has a double bond between these 2 carbons. All right, so we're going to eventually be able to draw things like when we do DNA and RNA, we'll see what are these collectively are called the carbon backbone of whatever molecule we're dealing with. Okay, and so it's a shortcut because it's a lot easier to doodle them like this than it is to write them all. So here's a water molecule. Here's the polar covalent bond that we talked about earlier. Again, you can imagine a line going through it this way. So it's going to be slightly negative over here, slightly positive over here. But the polar covalent bond is arguably the most important bond you're going to deal with in biology, because this is the bond that allows for weak interactions between molecules called hydrogen bonds. Okay. So you get a polar covalent bond when the 2 elements in question vary in their electronegativity significantly, but not too much, not enough to be ionic. Okay, and so the 2 that are really most commonly found engaging in these kinds of bonds are oxygen and nitrogen. All right, so here's just a few sample molecules, and you can go through this on your own, and you can look, figure it out, study it. The one thing I didn't mention was the Lewis dot structure. This is something you'll come across more in chemistry. And this lets you track the actual individual valence electrons in a way that's similar to the Bohr model where we do the electron distribution, right? But it's more shorthand, right? So it's easier to draw oxygen, like that than it is, or let me do that better. It's easier to draw oxygen like this, and hydrogen like that. So these are just varying shorthands, right? The same basic gist. Now, in addition to the forces that hold molecules together, the bonds that hold molecules together, the polar covalent, the nonpolar covalent, the ionic, there are other interactions at work between molecules, such as the hydrogen bond I just talked about. The key is these intramolecular interactions are much more weaker. They're much weaker than the ones holding the molecules together. And so here you can see a molecule of water interacting with a molecule of ammonia. All ammonia is nitrogen's water. In other words, you take oxygen with some hydrogens and you get your H2O, right? If you got nitrogen instead, you get H3N, or really it's NH3, right? It's H2O, but NH3. But the point is ammonia is the counterpart to oxygen in terms of the chemistry of oxygen versus nitrogen. And you can see here that like a water molecule, an ammonia molecule has a slight negative and slight positives. And the key here is the slight positive of the hydrogen interacts with the slight negative of the nitrogen, forming a stable but weak bond. And we see these bonds anywhere we see polar molecules. And our cells and our blood and our fluids are all filled with polar molecules, right? Water is the most common, but DNA, proteins, sugars, cellulose, which is made of sugars, there's all sorts of molecules that will engage in hydrogen bonding. So here's water. You can see a system of water molecules. You can see that as the water is moving, you can imagine this was a movie. These water molecules would be constantly vibrating, making and breaking these molecules, making and breaking all these hydrogen bonds all the time. Then lastly, this isn't in your book, but this is important. They're called van der Waals interactions. And the idea is this: if you take any two atoms, even if they're completely neutral, they're two completely neutral atoms, and you push them together close enough, what's going to happen is the nucleus of one of the atoms is going to not only, well, the nucleus of one atom is going to repel the nucleus of the other atom. It's going to push it away because they don't like each other. And as a result, the atom on one side is going to be lopsided and have a little bit of the negative charges over here. And that's going to attract that positive nucleus. And so there's a very weak interaction here. And so these things are nothing unless you have very large numbers of them. And there's lots of things in nature that take advantage of these. For example, if you look at the bottom, go back here. If you look at the bottom of a gecko's foot, you will see an incredible amount of surface area here from all the folds of the folds of the folds of the foot. And what that does is it gives the ability of the atoms in there to get really close to the environment. In this case, it's crawling on glass. It's able to stick on glass. In addition, if you've ever used a microfiber cloth, those microfiber cloths are so silky feeling because at the molecular level, they're really, really, really lots of surface area, and they will use van der Waals forces to remove dirt from whatever you're wiping with it, like your glasses. Okay. All right. So we already talked about structural formulas. I'll skip this slide. And now we can talk briefly about molecules and compounds. We can actually make definitions here. So a molecule, I kind of alluded to this earlier, is just a system of atoms. And you could say that the molecule is the smallest unit of matter that still retains the properties of a compound. So it's a compound. A compound is a substance that is made out of different elements found in fixed ratios. right? We've already talked about one a few times now, water. Water is a compound because it has more than one element. It's got oxygen and it's got hydrogen. And it's always found in a ratio of 2 hydrogens to 1 oxygen. Okay. So a molecule of water, as you can see here, is the smallest unit of matter that still retains the properties of that compound. So anything smaller than that, and it's not water anymore, then it's just oxygen and hydrogen. Okay. And so you can see here the difference between, say, ethanol, which is a volatile liquid that has some pretty significant biological effects, compared to glucose, which is a sugar. It's a solid at room temperature, and it's one of the most important molecules in our metabolism. You can see they're both made out of carbon, hydrogen, and oxygen, carbon, hydrogen, and oxygen. But look at the ratios. The ratios are completely different, right? And so different compounds, different elements, different ratios, different properties. And that's why you can now start to understand you have this very reactive metal, sodium, you have this very reactive gas, chlorine. You put them together, they react, and you get this very not reactive salt, sodium chloride. Right? Sodium chloride is a completely different substance than elemental sodium or chlorine. And you can't predict the properties of a compound based on its molecules, based on the different elements that make it up. Okay, so molecules like atoms have a shape as well. And the key to understanding the shape of any molecule is just understanding that when two atoms come together, those clouds of electrons surrounding them fuse together in a mathematical way to develop new shapes. And those new shapes we call hybrid orbitals. You don't really have to know anything about those unless you're taking a chemistry class. So you can look at now a system of atoms. In this case, it looks kind of like graphite. And instead of just looking at it as a bunch of carbons there, you can see them all now as hybrid orbitals, as all those electron clouds adding together and forming all these crazy little shapes that add up to one big shape. That's that. So let's take this home now. We're gonna now start to apply really basic concepts to the helping us with biology. And so one of the most fundamental questions we think about in everyday life, one of the most common things we experience in everyday life are the different states of matter. And you've heard of these your entire life, you know, solids, liquids, and gases. But what I want you to do this time is I want you to start with the solid, right? And I want you to imagine we're taking that solid and we're continually heating it up. All right, so we're going to add heat. And so let's start with the solid. Where do we begin? We begin with atoms that are not moving all that much, right? But here's the key. An atom, let's say this is an atom, atoms are always vibrating a little bit. They're always moving, undulating, vibrating. We call this their intrinsic energy. They have their own energy. All right, and that energy, that vibrational force, is going to want to pull it apart. It's going to want to have it move around. Okay, and so in a solid, those covalent bonds or ionic bonds that are holding the atoms together, or like in an ice cube, the hydrogen bonds between the water molecules that are holding them together, okay, are stronger than the internal energy. Okay, the hydrogen bonds are stronger than the internal vibration. They're not vibrating that much. They're cold. Again, think of an ice cube. All right, so when you're in this state, when you're in a solid, you can say you're organized, there's a defined shape, there's a defined structure. Solids have a defined shape. Now let's keep heating it up. Eventually, let's use ice. Eventually, what's going to happen is those hydrogen bonds are going to collapse, and the water molecules are going to start to roll around each other. They're going to just start to slide around and roll around. Think of a bag of pool balls. They're just going to slide around. They're going to be amorphous. They're going to not take up a defined shape anymore. A liquid takes the shape of the container it's within. If it's not in the container, it doesn't really take a shape. It just spreads out. Now keep adding heat. And what happens? Eventually, those atoms, those molecules will separate from each other. And so you get a gas, which is also amorphous. The difference between a gas and a liquid, though, is that a gas will occupy, it'll keep expanding until it occupies the container it's in. So it takes the shape of its container, but it expands. And then they start bopping into each other. And those are the three most common states of matter. You can get more exotic states, and the only one I'll teach you here is plasma. Plasma is when you get so hot, you keep adding energy, the electrons slough off of the proton and neutrons. It sloughs off the nucleus, and so you get this soup of nucleus and electron. And that's what a plasma is. If you've ever seen a bolt of lightning strike, that's plasma. Okay, so free electrons and free nuclei. That's that. So now let's take it home, because we aren't teaching, we're not learning a chemistry class here, we're learning a biology class. And so now we can start to focus more on biology. And we say, what elements on the periodic table are most essential to life? And most books will give you slightly different ways of organizing this information. The way your book does it is it'll give you the big four. And then it'll give you a list of some of the more modest elements, right? So you'll see here that 96.3% of life on Earth. Let's put it this way: take the human body, and then separate all of the various elements out, and then weigh them. You would find that if you weighed the collective oxygen, carbon, hydrogen, and nitrogen here, you'd add that up to 96.3%. And then if you took the calcium, phosphorus, potassium, blah blah blah, you get 3.7%. And then you get a whole slew of other elements that's collectively less than 1,000th of 1%, or rather 1/100th of 1%. And so we call these the trace elements, right? What I want you to know, memorize here, is CHNOPS, CHNOPS. Okay, carbon, hydrogen, nitrogen, oxygen, and then this is phosphorus and sulfur, which on the chart, they're not distinguished from anything. You know, phosphorus here and sulfur here. So again, you know, it's CHNOPS. Those are the elements that make up collectively a little over 98%, right? And the reason why phosphorus is so important, as we'll learn later, is this is the element that gives us the ability to carry energy through the systems of our cell. And then sulfur is important in being able to shape proteins. And there's some metabolic importances too, but really you can associate proteins and sulfur and energy and phosphorus. As for the trace elements, they do all sorts of things, but the simplest way to think of it is this: the trace elements assist our metabolism. They act as cofactors with enzymes, as we'll learn later in the semester. Okay. Calcium is important for our bones. I already told about phosphorus and energy. Sodium and potassium collectively are important to maintain the electrical gradients of cells, which help control the transport work, and it's essential for our neurons to fire. And then chlorine and magnesium are both essential for various things. We'll just leave it at that. Okay, now I already taught you isotopes, so this is kind of out of order here. I should put that in the beginning here. But this last part here, it talks about radiation. Here's the key. We talked earlier about carbon-12 and carbon-14, and we understood them as differing just in the number of neutrons. So I want you to imagine the nucleus of an atom as a mathematical shape with those electrons and those neutrons in there. And I want you to imagine that if that shape is ugly, if it's an ugly shape, like a weird 7-sided figure, whatever, and it's vibrating all over the place, because remember, everything's always vibrating. It's got its intrinsic energy. Slowly over time, something's going to spit out of here to correct that ugly shape into a pretty shape. And that correction is radiation. Okay, so radioactivity is when an unstable atomic nucleus emits some particle. You don't have to know the details of what the particles are for this class. Sometimes they're just photons, sometimes they're helium ions or helium nuclei. Okay, but the point is it'll get spit out. And there's 3 basic kinds of radiation. There's alpha radiation, there's beta radiation, and there's gamma radiation. Okay, and this is the order of their safety. Right, so gamma rays are very dangerous. Beta emissions not so good in high levels over long periods of time, and alpha is completely harmless. Right, so alpha emission can be blocked by a single piece of paper. Beta emission needs a nice thick piece of plexiglass, and gamma rays need a nice healthy piece of lead. So picture the alpha rays or alpha emission as a slow bowling ball being rolled to your feet that just touches you lightly. Think of a beta ray as a baseball being shot at you with one of those cannons in the batting cages, and it hits you in the chest and it gives you a huge bruise, and you're not happy about that at all. And then think of a gamma ray as a bullet from a gun. Okay, the reason why these are increasingly dangerous has everything to do with what it does to DNA, which we'll talk about later in this semester. Okay. So I just said all this. I'll skip the slide here. I'll pause. You want to pause it to read through this. You can do that. Otherwise, let's skip ahead here. So what do we do with radiation from a biological perspective is, well, we can use it in a lot of diagnostic tools. For example, you can see here this glow in somebody's throat, right? What they do is they take radioactive glucose, right? And then you drink it. Well, I think they drink it. I don't think they inject it. And they wait a little while. And the idea is wherever the glucose goes is going to be the tissue that uses a lot of energy, right? And so if you have cancer, cancer uses a lot more energy than other tissues around it. And so you get this kind of hot spot. That's a simple way to think about it. Now, one of the most important uses of radiation for biology is how we date fossils. We're not talking about carbon dating. That's one method of dating some biological samples. We're talking about radiometric dating. That's the generic catch-all phrase. The idea of radiometric dating is we have an isotope of some element that is unstable, and it decays to another element, and we can measure the half-life of that decay. And then we can go out into the world and we can find rocks that use these, that possess these various elements, and we can measure the relative ratios between them. Okay, because when the rock was formed initially, that ratio is locked into it when it's formed. So you can think of molten earth cooling down. The second the rock solidifies, that's when the unstable isotope is going to get locked there, and it's going to slowly decay like a clock. And we can use that clock to figure out how old that rock is, right? And we can use different isotopes at the same time, depending on the rock. The most common the most common clock we use in geology is the potassium argon clock, right? So the decay of potassium-40 to argon-40 is 1.2 billion years. And this is the one that lets us date the really old rocks. And this is the one that lets us say that the Earth is 4.5 billion years old. Okay. The other interesting thing you'll note here is there's a pretty thick line between, we have the aluminum magnesium clock of 740,000 years, and then carbon-14 at 5,730, right? And so, like, why aren't there any in between here? Why aren't there any clocks of, say 500,000 years, 400,000 years, 10,000 years? And the answer to that is we don't find that in the Earth's crust because they all decayed away to the point where we don't see them anymore. That's one of the most powerful explanations of an old Earth, right? So people used to think that the Earth was, 5,000 years old, no more than 5,000 years old. And there's people that today still believe that, despite all of the overwhelming scientific evidence. So this is the source of that evidence, one of the sources of that evidence. Okay, and that's all I'll say about that. So that's chemistry. You now can do the chapter 2 homework, and I'll see you in class. Take care.